again, I'd like to maybe go ahead and open it up the same way as yesterday, just if there are things that that some of the speakers would like to comment on that really stood out during the day, and that usually gets the discussion started, and then we'll start getting questions from the audience as well. So is there something that any of the speakers from the day would like to highlight or re-emphasize? Sure.
So from a hardware side, when I was listening to a couple of talks today, they've been mentioning that weights do not matter. So probably we might have to think of that differently. But when we're trying to design these things in hardware, that's one of the difficult tasks. So as a hardware designer, what should be the approach I have to take? I mean, should I consider the importance of weights in the design or not? So I believe you mentioned probably it could be just like wiring, dynamic wiring that could be building on. So if anybody could comment on that, I would appreciate it.
I can at least give the perspective that I had when I made the comment. I wasn't necessarily saying that weights didn't matter. What I was saying was inspired by Paul Rhodes' emphasis on growing new wires. The way that I think about that then is you can have weights whose values change, or you can have wires that come in and create new synapses, you know, perhaps with some sort of small value per synapse. So add more synapses with nominal value is another way to increase the effective strength of connection, right? But so from a computation point of view, it's identical. It increases the strength of a current to depolarize the cell. But from the point of view of the connection to development, it's very different. Paul is very interested, at my understanding, in how do things wire themselves up and make the connections in the development process. And so by generalizing from synaptic weight change to growing wires, it becomes inclusive of developmental wiring. That was my main point. But I wasn't trying to negate the importance of weights in a general neural net sense.
I don't know how long we want to stay on this particular topic, but just an interesting thing about development is that you actually grow an enormous number of weights that you then kill off. And you end up with far fewer weights in the adult than you have in the kid. And of course you're getting input all the time you're doing that, so it's not a blind process. It's trying to shape itself to presumably the distribution of things that it's seeing or hearing. Yeah.
Maybe just a comment on that. Potentially the system that we would be thinking about building would be able to do those kinds of things either in the software or in the hardware somewhere, so this system needs to be able to do those things at some point.
I would argue that from the standpoint of getting something that you can build, you probably need to have an architecture that's permissive of anything that you want to do, because it's probably a lot easier to inactivate connections, to run the weights down, than it is to create new hardware connections once you've got a system.
Just a quick note, one of the reasons I commented at all on development is because we have, I didn't talk about it, but we have a system that we're studying that is doing a developmental phase, trying to identify features that are in the input distribution, basically learning priors. So that you're identifying those features first, locking those in, and then you can't change them anymore when it goes to what we now call adult learning. So, and that's all software.
One other reason for being interested in the idea of adding new wires is when we think of adding weights, we're already coming from the point of view of we have a neural network and we're changing the synaptic strengths, right? The neural net paradigm has had its greatest successes in given a big pile of data that's inputs that have been hand-truthed by humans, learn the function that is embodied in the human, right? So learn to match this function. that is the surviving strong paradigm for what we mean when we talk about machine learning, I think. However, my favorite example is, I saw a tiger and it lunged at me at the zoo and it scared the heck out of me and I'll never do that again, right? The learn once from a very important event, which does not have the characteristic of a big database that you gradient descent upon. Now, I'm purely speculating, but that feels to me like a place where the neural net gradient descent backprop paradigm is not the right one for representing how we learn the massive major event that you learn this or die, right? Get it right this time, you don't get another try, right? And that one may, I think I've read recently about the growing of axons under these circumstances. So that's a big fear response, amygdala, flood with adrenaline. It's grow axons, similar to grow muscles under athletic stress, right? So it just suggests a different learning paradigm than increase the weights in a gradient descent.
Can't help it. May I have one? We often talk about three phases of learning. We talked about two of them so far, development and adult. There's one before that, which built the system that we start developing on, evolution. And it does, so there's built-in systems, and by built-in I only mean evolutionarily acquired, that are already wired to look for dangerous things, anything that gives you a fear response, and to immediately learn to respond to. And I agree with you. I like the idea that there's a list, a very useful list of things that machine learning isn't good at right now that I think can be future goals for work of this kind.
So there's this discussion of evolution and genetics and certain things being hardwired. Well, of course, there's all sorts of instinctive behavior. I mean, you walk along the pathway and you see a stick on the ground and you'll jump because you think it's a snake, right? I mean, there are people who are deathly afraid of spiders, and there's no, it doesn't seem to be a learned response. It seems to be a, deeply hardwired inside of them. And so there's this issue of the instinctual things that I think prove your point that there's genetic hardwiring of certain things that we have. But then, in your diagram, you had sort of the emotion engine separate from the learning. And it seems to me as though learning is very deeply connected to emotion as well. That motivation and issues around the emotions are a very tightly interconnected part of learning. It's the good dog, bad dog, or learning something and having some type of reward that then reinforces the learning behavior. And so I think that winds up being a very important part of these wiring diagrams.
Yeah, just a quick note of history. It was Jack Good, who was Alan Turing's assistant, who said, which seems always rung true to me, that it's better to start with a random network, because if you make it large enough, it will include every network you could ever need.
Yeah, I also like to make a comment a little more, putting us a little more close to the ground. I think that those are great ideas. To having systems that evolve connections and things like that, it's great. But it would be, I think, probably at this level that I think most of us work, it's more interesting to do online learning using reinforcement learning ideas and things like that. I think that this should be the goals, of, let's say, the next generation of systems. Because, when you start doing all of this, if you look at the traditional technologies, learning technologies, everything, we are still doing most of it, learning on, on batches of data. We hardly are at the point that we are starting to do online learning in real-time applications successfully. And I really think that those are great questions. I would love to have a system like that, right? But if I really want to accomplish a couple, certain goals, let's say in 10 years, in 5 years, that's not going to be my priority. That's what I want to say.
So there's a well-established computer science paradigm where if I phrase it this way, it won't seem so outlandish. So if I talk about growing new connections, I'm sort of making the implication of growing new wires. Okay, that does sound outrageous, and that's not going to happen anytime soon. Growing new virtual wires, so adding a new element to a linked list, certainly doesn't sound revolutionary, and we could do that at any time, right? So I actually remember having a conversation with Carver at one time about, he said, the hard part is knowing when to grow a new one, or knowing when to add a new element to the list, right? So you could imagine, for example, an existing Viterbi decoder for doing speech recognition that under some condition now gets the good dog reward, realizes it's learned a new word and adds a new element to the list. That's the computational equivalent to growing a new neuron or creating a new state. So it seems more reasonable when we put it that way. We don't have to actually add metal.
So how about the case of synesthesia or a blind person repurposing their visual cortex? You probably don't need to grow neurons in that case, right? So the network is there, and then the synaptic weights are 0 or 1, describing whether it's connected or not, right? So can't we just get down to binary, weights and agree that the network is the representation of knowledge rather than weights?
Just with the algorithm, MSC algorithm, as I think I pointed out, most of the connections do not involve weights. The weights are only in the memories, and the memories, depending on how dynamic they are, require something that could use a memristor, but it represents a relatively small number of small number of synapses. So really, it depends on the algorithm whether this technology is highly relevant or not, and this won't be determined for a good long time.
So I just have a comment on the genome or the evolutionary aspect. So I started off my career with evolutionary robotics. I did some of the first work in that field. I gave it up after a while because it came down to how being able to do the experiments that you need to do to gather the data to assess objective functions and then do the necessary. But something's happened since then, which is it's the creation of mass market robotics. Okay, so now you have vacuum cleaners. You have millions of them. We're going to have millions of robotic. You had hundreds of thousands of robotic dogs. You have all these things that can be replicated through mass production techniques, and now it's becoming possible to field maybe millions of things that can experience the world and then share that experience. And then the second point is that everyone knows that humanity has experienced this incredible increase in technology over a relatively short period of time, and that's probably generally because of the ability to pass information down from generation to generation and between individuals. So eventually these systems are going to have to somehow be able to, even as they're co-developing, exchange information, with each other as well. And I think that's going to really accelerate things.
So I'd just like to point out that on the arrays of oscillators that I showed this morning, I showed examples where all the oscillators coupled to each other are not. But you can certainly have situations where groups of oscillators couple to each other and they establish their own communication links simply because of the similarity in frequencies. And I know Hoppenstedt and Izakevich have a couple of papers out where they really propose that, where synchronization of oscillators in different portions of the brain establish the connection basically simply because they are oscillating at close to the same frequency. And that's what you'll see is that oscillator groups will tend to cluster together based on their own frequency. So that's another way to establish communication, just based on the natural frequency of oscillation of the various oscillations going on in the cortex.
Implicit in the question of dedicated hardware for synaptic weights or strengths versus virtual weights, having them in memory and running a processor that goes through them all versus dedicated hardware. Implicit in that question is fundamentally, to me, at its core, this is a power consumption question, right? If you want absolute minimum power, so for example, for the supercomputer folks, your 30 megawatt limit, and we need another factor of 10 in compute, and you can't have another joule of power of energy. What are you going to do? You got to do something to reduce the power. Well, okay, more parallelism, running things more slower, lower clock voltage, lower power supply voltages, and so on, leads you to less high-speed virtualization and more hardware that's just sitting there ready to deliver a weight. Now, that's in the early days in Carver's lab, we were doing analog VLSI. It was a dedicated circuit for every synapse, every neuron, and that was for sure going to be the lowest power thing you could do, right? But no virtualization then, right? Whereas you have the beauty of flexibility in virtualization if it's just a number in memory and you can make arbitrary virtual connections. So just wanted to sort of make that distinction. I almost see the community sort of split into the split, but without sort of discussing it explicitly, into the dedicated hardware for super low power purposes, and then the virtualized hardware for its tremendous flexibility and programming advantages.
So the paper I referenced that my student did, he actually compared those alternatives. So he compared hardwired. And when you scale up to cortex size, you can't use hardwired. You've got to have virtualized connectivity. You have to have address event. Otherwise, you end up with square meters of silicon. And so, well, but you don't need it. The thing is, the virtualized addressing gives you the same, actually gives you power savings on a significantly smaller factor. So, but he looked at all the alternatives, and what he found is that in the computation side, multiplexing, the fact that the network was sparsely activated, you only had to compute the neuron output for the neurons that received spikes, and so that virtualization led to a lot of savings, actually. So the whole, you still had small little processors, but each processor emulated a small group of neurons for the most part, and that gave, at least on the way he calculated the various price, performance, and power, that gave the optimal configuration for that model.
May I address? That's an interesting, really interesting point. So. The proof is in the pudding, or the details. The devil's in the details about how that calculation is done. If you assume virtualization, so P equals NCV squared F, if you assume that voltage and capacitance are being held constant, so you're just trading N and F together, you only get a first order effect. Basically, you've got fewer things, more things running more slowly. To first order, that's a wash. It's only a win if you bring the power supply voltage down because the thing is running slower. So if you may, some of you may recall my modest proposal from last year was 85 millivolt power supply is, requirement number one. Bring the clock speed down to 10 kilohertz, 85 millivolt clock, which is insanely sub-threshold. That changes the power computation dramatically. I'm sure there's no way that your colleague would have done that calculation because there's no technology in the world that runs at an 85 millivolt power supply. But that's what the brain is doing. That's why it's a win for the brain, but it's not a win for any technology that we currently have today. So there's an economic opportunity there. For example, I don't know how to address this, but if there are people here from Intel, things, or Qualcomm, the people who have their fabs, an 85 millivolt power supply that can actually do a digital gate. You're sitting at a gold mine there.
Trust me, people realize.
People are trying, right next to Intel, and so we know that, but it hasn't been done yet. So
hard.
Okay, right. So it's hard. It's a worthy goal.
Just a quick comment. I could say part of what we're supposed to be doing is being in the business of saying nasty things, right? Right? Who's with me? Right? Now, here comes a semi-nasty thing, which is the field of computer architecture has been very conservative for quite a long time. That's the least nasty way I know how to put it. So there's a world in between the standard processors that we have now for reasonable cost versus the extremes that we're talking about that go all the way to incredibly low power and or incredibly high parallelism. And if you want a modest proposal, I think there's a very interesting space of architectures that are doing enormous parallelism at what look today like ridiculously low power, not as low as you're saying. Oh yeah, yes.
Example?
Well, the ones that I showed. So I'll point you to papers. They're published and they're patented. I mean, they're out there. So and all they're doing is using very large numbers of virtual threads and running very slow. I mean, they're just what you would think. It just turns out this space hasn't been that deeply crawled over. It hasn't been that explored. So there's room for doing things that are unusual. And those hardware platforms are terrific for running the kinds of very, very parallel algorithms that we're doing, but that aren't all the way to 10 to the 11th neurons. They're algorithm level things, but very, very intrinsically parallel algorithms. So there is a space. Yeah.
Sure. So can I follow up? I want to connect one of your comments to something that Dan said. But if you would do this, you would end up with 100 square meters of silicon in 2D, right? But if you stack that into, slice that and fold that into 3D, now maybe what you end up with is 10 cubic centimeters of silicon. If it's low enough power, it can be done so that you don't have it doesn't burn itself up. So and that starts becoming more brain-like in a way that we also haven't discussed at the meeting. It's three-dimensional volume. The wires are now shorter. It's not 100 square meters of silicon with 10 meters on a side to get there. It's still, it's a shorter distance through a three-dimensional volume. So Rent's rule, and now you're limited by wiring, but that's a different problem. So that addresses the 2D space packed into a smaller 3D volume. The other key variable is the cost of the system. Up to now, the global minimum, the total cost of ownership has been lowest at the high speed. Take the next step into high speed, you've got a big performance jump, and it's only a tiny bit more expensive. Maybe it's even actually cheaper when we had Dennard scaling, right? But now, for the supercomputer Los Alamos guys, where the 30 megawatt limit, you cannot have another joule. I think it's opening up a little distant local minimum and the total cost curve over there, and I think it's a strangely deep one. And you'd never gradient descent your way over to that thing. You have to admit it's a whole different game. It's dedicated hardware, lower cost, three-dimensional, super low clock speed, or asynchronous, no clock at all, dedicated circuits. Completely different style of solution to buy the supercomputer guys the thing. And the only way it would ever be done in industry is if they're already, how much does one of these supercomputers cost anyway? The 30 megawatt power station that goes with it, how much do these things cost? This is $1 billion? Rough numbers. Few hundred million. Okay, so $1 billion here, $1 billion there. Right, so that's a big fraction of $1 billion. So the clump of, the pear-sized lump of silicon that would be insane if you had a pear-sized or grapefruit-sized piece of silicon that only did what a Pentium did, but it did it at 1 milliwatt instead of 80 watts, and you packed your football field-sized server room full of those things. Okay, what would you end up with? You'd end up with something that cost you $2 billion instead of $100 million, but the 30 megawatt power station would not be needed, and the air conditioner wouldn't be, right, exactly. So it's a totally different local minimum on cost and on power.
don't forget the design cost in doing that.
Sure, and the customer size is 3.
Three, yeah.
So in the end, this becomes something that only a government lab can do.
So actually, I kind of wanted to point to Kevin on that note as a connection. I mean, what's driving the supercomputers right now is not, I mean, high-performance supercomputing is actually a fairly small niche market. It's actually the consumer market that the microelectronics industry has exploded once the early requirements have been met. It's actually that maturation has opened up more markets. So actually, I wanted to see, Kevin, if the comments you had in your presentation in terms of the incredible market that's already out there, and it's being driven by the consumer market, and then just for almost no cost in terms of the additional functionality we can put into that stack to do some of these novel things. Actually, I wanted to see if you could expand on that or had some more comments.
So non-volatile memory flash is, their next target is really big data in large data centers because of energy efficiency and density. Once data centers start to care, I guess they already do care about energy efficiency, they're going to start converting to large portions of non-volatile memory. And we're noticing, beyond moving compute to GPUs, there's room for movement of compute through the whole stack all the way down to, the network speeds are getting fast enough that we're seeing more. You're not seeing a compute rack connected to a storage rack. You're seeing, storage and compute integrated very tightly, and flash, memory is enabling that as well.
So again, this is maybe not perfectly in terms of what's out in the industry right now, but there was an interesting statistic about Facebook. The data that's being uploaded right now, a user might upload, 100 images a day or whatever, maybe extreme user, but they only go back and retrieve only maybe 1 or 2 of them. So there's an incredible amount of data that's stored, but it's never accessed. So it's actually more expensive to store that on a spinning hard drive than it is on flash, maybe. So there are some server or compute data center requirements that are driving some of the structure of how those systems are being put together for the next generation. So again, if there's a way to then leverage that to some of the new computing architectures that we're thinking about or trying to explore, it's not going to be immediate one-to-one correspondence maybe, but there might be some interesting paths to pursue with what's coming out of there.
So I believe hard drives are still going to be orders of magnitude cheaper than flash. It's the random access. Flash write speeds are comparable to disk drive write speeds. It's that random access read capability that really helps the compute function. So and the highest storage density is still tape, right? So I think there's room in that whole hierarchy. Flash being, then the way I look at compute in flash, it's that layer just below DRAM before an SSD layer, which is before a hard drive layer. So that compute layer in flash is doing building models in real time, doing semantic tagging of that data, that high velocity, high volume data, and feeding that to the storage layer below, which could be SSDs or hard drives.
The eBay CTO gave a talk the other day, and he explicitly stated that for their workload, flash is cheaper than disk today.
So actually I wanted, maybe one more comment, and then I wanted to open up to the audience also.
I think the point that I would make in response to your questions about supercomputing is that I don't think that anything we're talking about here today are going to replace supercomputers for what they do. Right? We're really looking at different kinds of applications for which supercomputers don't offer a solution. But frankly, I'm not going to use my brain or yours to do 64-bit arithmetic. If that's what I need to do, then I've already got a solution for it. But if what I'm trying to do is to understand what I'm seeing in a gigabit image, then I have a really different problem, and I'm ultimately going to have a different solution. And ultimately, those solutions are going to talk to each other. You're going to have front ends that do sensory processing that then go back to databases that hold a lot less volatilely than the human brain would do it.
So I wanted to add to that comment in terms of probably the most powerful solution is going to be a hybrid where some of the things we're talking about here become part of the larger system where you do need 64-bit, 128-bit resolution on doing some calculation. That's the system we have at hand, but there are things that a system like what we're describing here might be able to do that the other system can never do, but when they're combined actually, that sort of gradient search kind of an analogy again, it's being able to sort of look over the landscape and say, jump over there, don't try to go this whole route.
So one extension of that idea is that, we talk about, the role of evolution. Right now we have genetic evolution that gives us a set of hardware, and then we have, social evolution that teaches us more and more about technology. But at some point, we're going to have evolution that allows us to build better systems than anything that we have, and then we can just replicate those. And then those are going to, serve as the bootstrap system that allow us to achieve even bigger things. I think that's inevitable. And I think we're already, in some sense, shown that that's happened, with the development of conventional computers.
Did you have a comment? Or?
Skynet.
I was trying to avoid that one, but it always comes up.
I just wanted to address, Winfried, your comment about flash being cheaper. So it's clearly cheaper from $1 per IOP or $1 per IOP per watt, but if it's just $1 per gigabyte, disk drives. So for the storage part of it, it should be, hard drives are cheaper, but if there's a significant amount of compute being done on that data, then definitely it makes sense to do it out of flash or other memory types.
So actually, I guess it's a response, so I'll come back next.
Thanks. I want to go back to the discussion about wiring forming. I remember having seen a paper which showed cross-sections of the brains of two rats, identical species. One rat was brought up in a very boring environment, and the other rat in a very challenging environment, lots of toys and so on. And the wiring of the rat in the challenging environment was dramatically denser. You guys looked at it and see it was maybe 5 times denser. So I think there's no question that the wiring changes. Do I have time for a pedestrian question? Yeah. Today we heard again and again that spiking reduces energy consumption, but I'm chewing on this. Let's assume we have a transmitter and a receiver connected through a wire, and they are implemented in CMOS. And in traditional CMOS, it's only the transitions, right, which can require energy. So if I want to transmit a value with, say, an accuracy of 1% across this wire, and we do it with ordinary encoding, then obviously 2 to the 7 is 128, so we need 7 bits, 7 transitions or whatever. Now if you do it with spiking, when it's frequency encoding, for 1% transition, obviously we need a frequency up to 100, compared to from 0 to 100. So in the worst case, that is 100 spikes, or on the average 50 spikes. In the former case, the average of 7 is 3.5. So that would argue that the energy needed in spiking is, in this my example here, with 1% accuracy is about 14 times higher. So where's the mistake here?
Maybe before turning it over, I'll try. I think, rate encoding on a single wire is definitely the way you're describing. You'd have to do all those transitions on that one wire to transmit that signal. I think at least the way I've been envisioning the system, it's really not information transformation on that single wire, but it's the ensemble activation of a unit in a network, actually a group of units in a network that's actually representing that number or that value, rather than that value being transmitted across a wire. So it's still, in the end, it's a single spike that's being transmitted, but it's maybe 5 spikes that activate 10 units in an area of, let's say, 1,000 units. That's representing that number. It's not the data that's being transmitted on a single wire. So that's one interpretation. I don't know if there's...
In most systems, the cost of transmission is the dominant one. Yeah.
Let me come here and come back.
So, in the very first stage of the auditory pathway, there's an example that actually that is extremely important and extremely relevant. So the signal that reaches any single inner hair cell has a total dynamic range of about 30 dB. Right, so sort of factor of 1,000 that in signal range that it needs to represent. And if it was to do that with a single axon, then you'd have the situation that you just described. And encoding that with spikes, you'd sort of have to count to 1,000, range of like that. That's not how the auditory system does it. Each hair cell synapses onto 10 spiral ganglion cells. So you basically have 10 wires to represent that one thing, that one signal, half-wave rectified signal, and each one of those 10 signals, the spiral ganglion cells have different thresholds. The net result, to first order, it's like you have a 10-bit A to D converter. You have one bit with a higher threshold, so you need a big signal for that one to spike. So to first order, I explained that to the people that worked at audiences, like, okay, no, it's really like a 10-bit A to D converter that happens to be represented with a spiking communication. The nervous system, one of the fallacies or the traps is to say, I stuck an electrode in and I measured spikes, but to not have the context that while you were doing the equivalent of reading the second most significant bit of a 10-bit bus. Just because you saw spikes on a wire doesn't mean you knew the meaning of it. But in that one place, because we could see that it all originated from a single hair cell, you could see, it's a 10-bit bus. I think that kind of thing is prevalent throughout the nervous system, but once you get up into the brain, you can't decode it because they don't come in groups of 10 anymore.
Maybe just to, might not be the exact follow-up to that, but Jeff Lichtman at one of the workshops just a couple of weeks ago gave an example of that. If you look at two neurons that are sort of an axon and a dendrite, they're sort of wrapping around each other. Usual thought is, well, there are maybe 1 or 2 synapses between this neuron and this neuron. Turns out it's more like 8 or 10. And they all have, some of those are active, some are inactive. So some of the earlier theories about, well, there's only one connection and there's only one weight, it's probably a lot more complicated than that. And some of the, so let's say 2, 3 synapses were sort of seen and kind of assumed, but on the average going up to 8 or 10, and how does that actually, what was the implication for how the network is formed or how the network is functioning is, I think, just recently being debated or is being actually seen.
I would say that the other thing that contributes to the efficiency of spike-based encoding is that, in general, you're not encoding individual pixels. You're not using 8 bits to define an intensity value that you see at an individual pixel. At least by the time you get to visual cortex, you may be representing a neighborhood of 60 by 60 pixels, and you're going to represent some basis function, some eigenfunction with 1 bit that denotes the presence of an entire pattern. And maybe you need 3 or 4 to fully define what's in that patch, but still that's 3 bits relative to 60 by 60 by 8 bits. And so I think that's one of the places, it's in the representation where some of the efficiency actually is realized.
I want to throw out 2 ideas, and there's plenty of detail that could be argued one way or the other about this, but let me just toss them out for you. One, what if spikes don't convey state as much as need for action, need for change, or error? And two, what if synapses aren't simply the connection between neurons, but the essential computational unit in the neurons simply exists to move signals from synapse to synapse?
I guess I would say that there's evidence for both of the things that you say that they're in fact true. I mean, it's not the whole story, but synapses are arguably the basic computational elements. They are the things that, that convey a signal from an input bit to actually a change in the amount of current that's flowing into a neuron that's changing the membrane potential. And mostly what is signaled are either things that represent a change, either a temporal change or a spatial contrast, or a need, or probably, as we understand how prediction and extrapolation occurs, we'll find out that it's an error message as well.
So we've heard talks from a huge array of people all the way from neuroscience to hardware and software architectures. And there seems to be this clash sort of between the level of detail that we should take. So neuroscientists tend to take more and more detail because it's hard to test hypotheses at the high level, whereas system designers want less detail so that it can be more scalable and more tractable, either in software or hardware. So one application of these neuromorphic computing systems is possibly to test hypotheses about large-scale neural systems. And I'm wondering if you could comment on the validity of those approaches, or you think it'll ever be valid to test neuroscience hypotheses on artificial substrates.
Really? Well, let me say this about that. Brains aren't the only thing where we don't know which parts are crucial and which aren't. There's loads of evidence that we don't need 5 fingers, and we don't need, hair in certain places on our face. We don't need, eyes above our noses. And we don't think about that stuff. And if you look in the fossil record, none of those things that I ever described have ever been tested. So it's not that we've generated a bunch of these possibilities and tried them out and watched them fail, but rather that they never got tried. So the thing you're suggesting is something that actually hasn't even happened in evolutionary time, interestingly enough. It's as though, and people talk like this, it's as though genes are immensely constrained. They can only build certain things. As soon as you start to make changes to them, most of the variants are stillborn, and so you never try most of the variations. Brains are just body parts. They're gonna have the same kinds of characteristics, and it's going to be pretty. It's a vast space to examine. One of the ways to go after it is not a near-term thing. Is to look at what genes actually can build. As we start to understand morphogenesis, how genes actually do what they do, actually build organs and organisms, we'll have a very different sense, I think, of what kinds of structures have actually been tested. I see you gesturing. Yeah, go ahead.
So the point that I would make about genetic evolution is that it is a highly constrained process. As you say, what you can't afford to do is to get rid of something that's working in order to try out something new, because almost all the time that's going to result in the organism not being viable. So what evolution does instead is it replicates things, and then it has kind of a free rein to play with something that's not essential. And so essentially all the functions that you get come from this process of changing something, then playing with it. You know, you get a new biochemical function, maybe you double the thickness of cortex. And there are lots of kinds of things that happen. But in reality, there's a whole lot of genetic baggage that we keep around just because we haven't had the flexibility to get rid of it.
I guess I had a different take on your question. So, I thought it was the question along the lines of can a artificial system be a model of a biological system? And so there's an interesting paper by Barbara Webb, and she raised the question: can a robot, for instance, be a model of behavior? And there's it's a BBS article. I suggest, I highly recommend reading it. And she makes the case that I think that if you're trying to get at the neural basis of behavior, ultimately you have to build sort of synthetic systems. Robots, the topic of her paper, aren't very well accepted as part of a biological experimental paradigm, to say the least. But you could say the same thing about computational models, and she makes the case that, well, a robot is really a piece of technology that you're using to base your experiment on. All things you have are models in some sense, and they can be instantiated as a mathematical model, as a computer model, as a robotic model. And so you shouldn't look at a robot or a system with a lot of neuromorphic elements as a less legitimate expression of a model than anything else. And so I think it's just going to take some time, and there's a lot of baggage, I think, that biologists bring along with them in the way they think about the world.
I think this is actually a very important question on which degree of complexity of biological cells is necessary to achieve the computational performance that we would like to see in our artificial system. And I think the question is so important that it needs a very, very systematic approach rather than guessing. And I mean, one of the systematic approaches which I would suggest and which we are actually going to do in the Human Brain Project, I will talk about this tomorrow, is that we do two things in parallel. I mean, there is the computational neuroscience approach where people actually put extremely detailed model on high-performance computers, really building extremely detailed models of cells with thousands of compartments, with individual ion channels, even with glial cells, where we don't know really what the function is. So you put in everything you know from biology, and you run an incredibly complicated simulation, which is slow, which is extremely expensive. It uses tens of megawatt to do. But then, of course, you have sort of the extreme case. And then the next step would be to take out the complexity step by step and see at which point are you losing certain features, certain computational features. And that's where you stop and then implement into the simplified system. So that would be one way to systematically approach these things.
There's a question?
Well, I guess one interpretation of what you suggested also is do we need more interaction between neuroscience and engineering? And I think that's actually something that's very necessary, because otherwise you run into this problem that there are these neuroscientists, 30,000 of them. Yeah, they do something and we don't know how to make sense of all this data that they're collecting, and on this side, we're building whatever we want, and when we get to the part that we're writing the introduction of the paper, then we call them and says, is this correct biologically? And one of them say, yes, I've seen this before, and then that becomes so I think perhaps the separation between these two is a little artificial. And I guess we are in a very unique position, because when you try to build something, that's the only time that you know which parts are difficult, which parts are easy. So we can actually form some very good testable hypotheses that then we can go and test in the actual biological system, and that would advance both of them.
Question was?
I just wanted to respond to your suggestion, which, I mean, I absolutely agree if your objective is to understand how a neuron or how small groups of neurons work, that it is possible to do that kind of simulation and to systematically deconstruct it and to ask whether or not any particular feature is relevant for the function of that cell. But I would argue that the difference between between a brain and a small set of neurons is that there are behaviors that really do emerge from the interactions of large numbers of representations. There are aspects of neural encoding that were missed for decades because people studied one neuron at a time. And so, so in order to address those kinds of questions, you do have to step back and say, okay, maybe I don't need, 25 different ion channels. Maybe I can get by with a simplified neuron, because the level of the question that I'm trying to ask really is about interactions between large numbers of neurons, populations, rather than interactions between individual cells.
Just a short answer. I'm not proposing to simulate a single neuron at a detailed level, but really going to a network. I mean, this is why we actually need the very, very high-performance computers to do those simulations. But I mean, these high-performance computers, there will be maybe 1 or 2 or 3 in the world. These things have been said many times. I may be as wrong as other people, but of exascale computers, we will not produce many of them, but at least one of them will be needed for brain science, that I'm convinced of. And the results will be very, very important to do this consistent and systematic complexity reduction. And then hopefully we can get to systems which are cheap and small.
So I just wanted to offer a few comments about hardware and experiences in the Synapse project and sort of what the challenges are. There's sort of some hard constraints here in building the hardware. The first thing to recognize is that the synapses are the problem in all of the architectures. They're the problem. They take up all the memory. They're the thing that we really don't know how to do very well, because presumably that's where the learning rules are. The neurons are all pretty simple. You can do different neurons. You don't end up using so much space on the chips and so forth. It is a big challenge doing the routing of the signals among all the different items on the chip. I'd say, in IBM's case, that's probably the biggest fraction of the hardware engineering goes into the routing network. How do you get signals from place to place? The challenge there is, once you lay down a network or an architecture for routing signals, you necessarily limit the kinds of networks you can build. And so you end up making some hard choices when you go out to actually build a piece of hardware. The other thing is that you really need a lot of memory on the chip where the processors are. This is a huge problem. And maybe, I know some of you know this, but throughout the Synapse project there were efforts going on in alternative memories of various kinds. And I think some very good things came out of it. There's a lot of very good work, I think, going on in the field of memristors. I think we heard some of it today. But still, it's a really long path to go from a new memory technology, in a laboratory to something that's in a state-of-the-art logic fab. It's an extraordinarily long and expensive path. And it just wasn't going to happen in the time duration of the Synapse project. That's for certain. Also, to get that kind of technology into a fab, it needs a very large existing market to sustain it and create the investment for it. So there was really no path to actually doing that. To HRL's credit, though, they actually did do it. I mean, they actually did put memristors on CMOS, do the whole 9 yards, plastic synapses, routing spikes and everything. But it was quite heroic, and it wasn't clear, it still isn't clear how to best take advantage of that commercially or in a large-scale application. So when you go, when you confront this hard problem of memory, and you say, gee, I need a state-of-the-art logic process too, because, I got to have all that to do all the other things I need to do, the routing and the computation and so forth. Then, unfortunately, you get stuck with SRAM. And SRAM is okay, but it's big. We talked to IBM about doing embedded DRAM and so forth, and that was a hard thing to do, so we didn't do that. So you end up with, you build a state-of-the-art CMOS chip, and you can get maybe, at least when we were doing it, half a gigabit, I guess, of SRAM storage on a very large chip to use as synaptic memory. So anyway, there was just a lot of challenges there. And then, again, you remember I was saying yesterday, one of the hard things is that there's not a clear evolutionary path for the technology where even when you build this state-of-the-art thing, right, that I just talked about, and let's say it did even more than all the things that were accomplished in the Synapse project, incorporated some of your favorite features that they don't incorporate now. Still not clear you're quite over the hump for the application space, you know, for, I mean, I can imagine a few things in robotics we could do because I worry about that all the time, but sort of in vision processing that takes a massive amount of processing to do a lot of that. So anyway, those are just a couple of comments about the hardware challenges.
And this is only to echo what the points that have been made already, but I think one of the problems that we've encountered is that trying to do state-of-the-art algorithm development on conventional hardware, is also not going to get us there because we need to do things that we cannot realistically or reasonably do, with systems that have the constraints that we have. So, there really is the chicken and the egg problem. I don't see any other solution than some sort of co-design kind of strategy where you're sort of bootstrapping both the underlying technology and the algorithms at the same time.
And that's the reason why we're bootstrapping our program off of a memory development. There's the cost of developing a new technology is just so outrageous. I mean, even if you put all of DARPA's budget into it, it wouldn't cover it. So and that was like a shock to me when I finally figured that out. So there's this issue. You've got to find something that you can piggyback off of that's climbing up the road to commercialization and have that drag you along with it, because there is not enough research money in the country to actually fund something like that, to take it from idea to a really hardened working prototype.
Just wanted to comment on that. I mean, just to give a range of resources, one of the latest 300 or 450 millimeter fabs going in is on the order of $7 billion to $10 billion, and that's going to run an established process in terms of getting something up to level of maturity that's needed to go into that kind of a production facility and to be able to produce the numbers needed. It's a huge amount of resources. I mean, it's a really hard challenge.
Yeah, Gordon Moore always said that Moore's law will end for financial reasons. Just the people that invest in fabs are going to make the decision at some point they won't get a return on their investment. That's that. And that's the problem with exotic devices and stuff too. It falls in the same category. In the Upside program, we have an exotic device component, but we also have a traditional CMOS component where most of the actual results are going to come, I think, for that reason. The exotic devices are there to maybe prove some feasibility, which may down the road lead to something. And I think that's kind of what we can do with the memristor work that people are working on now.
I completely agree with the idea, the importance of piggybacking on something that is already riding Moore's law, or riding commercialization to increased volume. So if you can piggyback on that, then you're surfing a wave where the wave is behind you, pushing you forward, and it's easy to go. The other thing we have some experience over the last 20 years was not only do you need the technology working in your favor, but you need to have a programming paradigm or a deployment paradigm that is not too radical a shift from the one that's before. You can have some incremental change, but so in particular the experience was in the early 90s trying to commercialize analog VLSI. It's not like there weren't lots and lots of smart people who were behind that, dedicated to it, and industry precedent. Intel was behind it for some time. The ETAN project, Ron Benson was associated with the Caltech lab. the combination of needing a different fab process, needing highly skilled, esoterically trained people who only could do that thing, and you couldn't just sort of write a C program to program your chip. You needed analog VLSI designers, and there were only 30 in the world or something with that thing. So it's important to remember the need for staying incrementally close. You can evolve with support if you're close to an existing paradigm. If you're too far away from it, you're cut off from it and you can't survive.
And you even... I would like to ask, since we have here an expert, okay, in Van Neumann, it's an interesting question. So what was, the funding, okay, that went to be able to create something radically different from anything else, right? Right? So what had changed, in this path of history? Do you have
it was a little under $2 million spread over almost 10 years. And the way it worked, the best description was just they had a meeting once or twice a year and they just passed the hat. They met with the counterparts of the agencies and, well, Joe, can you do 30,000? And they got the money. The Army, first it was under the Navy, and then it went under the ONR, then it went under the Army who could move quicker. They could write checks faster, but they wanted reports. And then it went to the AEC, who didn't care about reports. So it was all very easy. It seems like sort of the golden age of just get the thing done, and it worked.
But in terms of today's dollars, how much is $2 million at the time? I mean, I just would like to find out what happens. Or is this really a slowdown because of the technology complexity that we are effectively bringing into the table when we start new ideas and things like that? I mean, it's an interesting question.
So the venture capital community is behaving differently around semiconductor investment as well, too, for different sets of reasons. One of the lead investors that funded the company that I founded 10 years ago said we wouldn't fund your company now because basically it took 10 years and $70 million to get something that was worth $300 million, right? So that kind of return on investment, it's not a very big return. They're looking for a 10-bagger in 4 years, not a 3-bagger in 12 years. Right? So the return isn't great enough, and the fact is there was a risk that it could have been worth nothing. That is common, right? So just sort of the scale of the investments, the desire for shorter-term payback means that sort of the investment community behaves differently, and we're seeing something similar in the military community, presumably as well too. But the easy money is not where it used to be, I guess.
But I also think some of it is that it's very hard to compete with commercial silicon now. I mean, the opportunities for niche silicon they're getting smaller. You found one.
We found
one.
Yeah.
I tried to find one,
but it was a
rare
lucky find.
Yeah. So that's part of the problem too. Intel puts 1,000 people on a chip, and it's the densest process in the world, and you can't.
We built our first with a team of 5.
Yeah, you can't compete very well against that, and so.
Yeah, I'll just mention one other thing when you talk about start introducing radical new technologies to an existing process. There's not only a lack of support, there's an act of inhibition on the part of the fab. You try to bring in some of these new materials, the fab manager won't let you within a mile of his fab with some of these new materials. So introducing a new process or a new material into an existing fab and trying to leverage technology that's already there is extremely difficult. You don't want to kill the existing process and to get something that may or may not work.
And then along those lines, one of the weird things is for your end customers, if you've got to actually sell to people out on the streets, you have to do your best to disguise a revolutionary technology as an evolutionary advancement so that people don't get scared of it. And I think that they don't even want to come close to buying it. So, I mean, you know, the system does not like change. It doesn't, and especially doesn't like big change.
Right, but I would also say that to a very large extent, the early development of computing systems were driven by just fear, right? We've got to build a bigger bomb, you know, we need to make it work. It doesn't really matter what it costs. And I can say that's not the mentality at Los Alamos anymore, right? You know, you couldn't do that now, and it's because there's a completely different set of budgetary constraints and a very different set of motivations.
I'd like to tell you a story. I mean, when preparing the Horizon 2020 program in Europe, there was an opinion poll among the scientists what they would expect from the new program. And guess what was on top of the list? It was not more money, but it was less reporting. And it didn't happen in Europe. I mean, it can tell you it got worse. But I can almost promise you, I mean, maybe you can take that as an example, but what George just said, I can almost promise you if you reduce the amount of reporting, I'm sure that more will come out of your dollars that put you into this research. Europeans did not do that, unfortunately.
So maybe one last quick comment, and then we'll go ahead and wrap up.
So I guess the last discussion we're having kind of paints a pretty rough picture, right? We don't have the technology. We're not possibly going to get the funding to actually get there. And then somebody like Dan has to go say, well, we're going to have this new stuff that would really help you. I guess it suggests that we have to use more of the conventional stuff and try to understand the function of subsystems there to understand how they work before we get down to the total, you know, very detailed kind of thing. Because, you know, the big things, I think other than the Manhattan Project, the trip to the moon was sort of the other example of how you make a huge change. And it only happened because accidentally the NASA administrator screwed up and got 4 times as much money as he thought he needed to do it with. So, you know, instead of getting, I don't remember, it was like $2 billion, they ended up with $8 billion. And they barely made it. So this isn't happening today, so it's going to have to be a more gradual. But I wonder if you actually agree with this kind of, that we have to really work a lot more on the subsystems to try to understand and hope that there's a tractable number of subsystems that make up our brain so we could simulate them and figure out what to do with them.
So I agree with that. I mean, the last company I built was funded to be a chip company and did so. The next one, I don't believe will be that. And so what am I going to do? I'm going to simulate things on existing hardware, try and ride things, existing technologies that make sense for prototyping at scale. If anything, the last company, I told investors I want this to be like the NVIDIA of sound input, right? You know, we're going to do hardware acceleration for sound input instead of graphics rendering, and that resonated with the investors, and they bought into it. Now, if anything, so the next company now I suspect is going to look a lot more like Google at its beginning. Scales nicely. You know, you want some more compute, add more PCs, except so that kind of scalability. It doesn't need $70 million before the first thing starts working. I can self-fund this thing. $300,000, you know, buy racks of computers and let them be low-power ones. And there's lots of places to find low-power ones that are capitalizing on existing technology trends that may look different than what Google did 20 years ago, or 15, whatever it was. So anyway, so I think it will look different. Every technology, every opportunity is born in its day, It's not Manhattan Project now, and it's not Y2K right now. It's 2014, which has its own unique opportunities. So something will happen, though, for sure. We'll look back 5 years from now. There will be some phenomenal commercial and technology success that we will be able to identify 5 years from now. We'll look back and say, wow, that guy spotted it and he nailed it. I hope to be that guy, and I hope, I hope for all of us that we can have that kind of success. But that something will happen, and our job is to spot that opportunity that makes sense now and only now.
So maybe really quick comment, and then we'll wrap
really
up.
quick, just to address your so I would argue that the other game-changing technological achievement of the last 20 years is the Human Genome Project. And the way that was accomplished was not by, saying, just throwing a lot of money at it. It was up front, okay, we need to do this smarter, right? We're going to use existing technologies, but we're going to do it smarter. And sure enough, it comes in under budget, under time, and delivers technologies that now make gene sequencing, a commercially viable enterprise.
So I'll add one more detail to that. The Genome Project, as it actually started in DOE, and it got to where it got, I'd say, because of Craig Bentner, at some point said, not that I'm going to do this. He took off, did it in a different way than the established project. And so there are some breakthroughs that somebody spots something and takes off with, and that actually drags the rest of the field with it. So again, I'd like to thank you all. Thanks to the audience, and hopefully we'll have a little bit. Again,